Okay, this problem is homework 9, problem 5. Problem 5 states a 0.113 kilogram ball is thrown straight up 1.94 meters above the ground. Its initial velocity is 6.4 meters per second. Short time later, it hits the ground. Calculate the total work done by the force of gravity during that time. Okay. So we have a person, right, holding a ball. That ball is initially at a height of 1.94 meters off the ground. It's thrown straight up in the air with a velocity, an initial velocity of 6.4 meters per second. So the ball goes up. At this point here, it has a velocity of 0, right? Because it's going up at 6.4 and it's slowing down as it's going up. So it slows down, slows down, slows down. The velocity then becomes 0. At that point, it switches directions and comes back down and hits the ground, right? So it's asking us to calculate the work by gravity. So work, again, is force times the displacement. So there's a couple ways you can solve this problem. Work is force times displacement, and it is also, work is also equal to the change in kinetic energy of an object. The change is just the kinetic energy final minus the initial kinetic energy is the change. That equals work. So we can actually solve it with either one of these. But the way to think about this problem is that the ball is thrown up at a certain velocity of 6.4. It reaches a velocity here of 0, and then it falls back down. And at this point right here, so basically the exact same point, that's not the exact, but the exact point on the horizon, in which it was thrown up at, once it reaches that spot, the velocity here should equal the initial velocity. Because it went up at 6.4, it reached a max height, and then it came right back down. And so the gravitational force that's slowing this ball down to get here is going to be the same gravitational force it speeds it up from going from 0 back down. So this velocity here should be the exact same as the initial velocity. Now the person is standing here, and this is the ground. And so this initial height off the ground was 1.94 meters. So what is the change in the kinetic energy if we say this is situation A and this is situation B? Like, what is the change in kinetic energy comparing A to B? Well, change in kinetic energy is the final, right? So we'll just choose B as the final, B, minus kinetic energy initial, which is A, right? So kinetic energy is 1/2 mv squared minus, and so this is v naught, because that's your initial acceleration. Or you could also say A, the velocity at the A reference frame, and 1/2 mv squared at the B, right, or the B reference frame. So it's talking about this velocity. Well, intuitively, we can tell that this should equal 0, right? Because our initial velocity was 6.4, and our final velocity should also be 6.4, right? If you square that and you have the mass is the same, all divided by 1/2, then this value, whatever this value is, should be the same as this value. So it's that value minus itself. So it should come out to 0, right? So the change in kinetic energy from from B to A is equal to 0, okay? So, but our problem doesn't say what is the kinetic energy when it reaches this point. It says when it hits the ground, right here. So, what is its kinetic energy here? This is our final kinetic energy that we're trying to find. So, the kinetic energy, again, we're going to call this C. And just so I can keep myself straight here, I'm going to redraw it. So we have a person threw a ball up, and then that ball came back down, and then it continued until it hit the floor. Okay. It had an initial velocity of 6.4 meters per second. At this point here, the velocity is equal to 0. At this point here, the velocity should equal 6.4 again. And this, we're looking for the kinetic energy here. So we know that the overall kinetic energy at this point, the change in kinetic energy was 0. So let's choose, we'll say that this point here is going to be A, right here. This point here is going to be B. So the change in kinetic energy is equal to kinetic energy final, right, or B, minus kinetic this is not deltas. Change in kinetic energy is equal to the kinetic energy final minus the kinetic energy initial, which is A. Okay, so what is the kinetic energy here? We know kinetic energy is 1/2 mv squared. So that's the velocity at the A reference frame minus, B reference frame, minus 1/2 mv squared. And this is the velocity at the A reference frame. Okay, so we know the velocity here. We just said it. It was 6.4. We don't know what the velocity is here at the end, okay? But we can use kinematics to figure out what that velocity is. So what I would probably use is delta y is equal to initial velocity plus acceleration and time. Actually, this is probably not the best, but actually, let's don't use that. We're gonna do V final squared. I'm trying to think of these off the fly. V final squared equal V naught squared plus 2A change in Y. We're gonna use this kinematics. And the reason why I didn't use this one is because we know this, and we know the acceleration, and we're gonna end up with time. But time doesn't really fit into this equation. Like, we don't really need to know how long it took from it to go from here to here. We really need to know what the velocity was when it reached here. So a better equation is velocity equals initial velocity squared plus 2 times the acceleration and the change in the y. So the initial velocity is 6.4 squared plus 2 times 9.8, which is the acceleration due to gravity. And the change in y is when it crossed this point to the ground, which is 1.94 meters. Okay, and that is squared. So then we take the square root of both sides, and we should get a final velocity of 6.4 squared plus 2 times 9.8 times 1.94, square root that whole thing. So that value is 6.4 squared plus 2 times 9.8 times 1.94. and then we take the square root. And so the final velocity is 8.88729 meters per second. So that's how fast the ball is when it is at this spot, when it hits the ground. So it has a V at this spot of 8.88729 meters per second. Okay? So going back to here, we know that it's the change in kinetic energy is 1/2 the mass of the ball, which was what? It was 0.113, I think. Yeah, kilogram. And the velocity at this point, the final velocity, which we just calculated, so that's this, squared minus 1/2 times the mass times the initial velocity, or the velocity at this point, which was 6.4 squared. Squared times 0.132. So for this side of the equation, I get 4.4626 joules minus minus 2.31424 joules. So the overall change in the kinetic energy from point A to point B is 2.31 joule. Actually, I did my math wrong here. So for this first portion, I actually got 0.113 times yeah, I actually got 4.462596 joules minus this part, which I got 2.31424 joules. So the overall change in kinetic energy from A to B is the difference between those, which is 2.148 joules. And we set up here that work is equal to the change in kinetic energy. Okay? The other way you could have solved that is with the other theorem, right? So work is equal to force times displacement. Person throws the ball up in the air, and it comes back down, and then it travels again, and it hits the ground after traveling 1.9, it's 4 meters, okay? So work is force times displacement. So what is the force in this scenario? Well, again, force is equal to ma, and our A is the acceleration due to gravity, and our mass is the mass that they gave us. So that is the force in this scenario. So if we take a snapshot and we go person, threw the ball up, back down, when the ball is here and it's traveling to the ground, okay, the force in this spot is ma, which is just equal to the mass times the acceleration due to gravity. So 0.113 times 9.8. So the force acting from here to here is 1.1074. And we know that work is equal to force times displacement. So if we say work is equal to this value times our displacement, which our displacement from here to here was 1.94 meters. So 1.94 meters. That comes out to being 2.148 joules. And that correlates to what we got. Oh, wrong paper. But that correlates to what we got initially when we had calculated it this way with the change in energy. So you can find work with work equals the change in kinetic energy, work equals force times distance or times displacement.